Okay. Pardon the quick slide deck. So we were talking last time about various defense mechanisms against buffer overflows and stack smashing attacks. Before we go into that, one of the things that I want to do in this class, I hope that people would do it as part of their class participation, but nobody has volunteered yet. So is to talk about computer security attacks that come up in the news, to sort of walk through them a little bit so you see what's happening. There was a podcast on one of the first computer security attacks from 1834, or network security attacks. It was an attack on the French mechanical telegraph system, where the telegraph system could send messages at about 1,000 miles an hour through flags on the top of hills. You know, this would be an A and that would be a B. Somebody figured out that this meant that normally stock market prices would take 5 days to get from the north of France to the south of France. Somebody figured out that if you could inject stock market prices into the military traffic, you could get stock market movements early, make a bunch of trades, and make a lot of money. This is now called high-frequency trading, but it started in 1834. So, because the original telegraph system was really just for military communication. So somebody bribed the telegraph operator and said, if the stock market goes up, then insert a Q followed by a backspace into the traffic, and if the stock market goes down, put an R followed by a backspace. Then in Toulouse, you know, there's these, in south of France, these flags are up on top of hills. Anybody can look at them. So the attackers would just get out their telescope and look at the flags on the top of the hill. And if they saw the, Q followed by a backspace, it would mean one thing. R followed by a backspace, they know the other thing. The operator who receives it would assume there was an error, remove the offending characters, so the military getting the message wouldn't see anything wrong. And this led people for 2 years figure out sort of how stock market was moving and make a lot of money. Any guesses as to how this scheme was broken? What happened? And it's sort of a lesson in computer security as an attacker. Yes?
Did the person who got bribed tell the stories?
He did not, but you're very close. What happened is he got sick. And so somebody else replaced him, and he told his replacement about the scheme and tried to pay the replacement. The replacement was honest and went to the authorities. Yes. So the takeaway from this is that as an attacker, you have to be very good to not leave any tracks. And it turns out there's a lot of attacks that are figured out because an attacker gets sloppy. So an example is the attack on the Democratic National Committee that hacked into John Podesta's email. It turns out that one of the attackers forgot to use a VPN one day and happened to log into a site directly from Moscow instead of logging in through a VPN server in Romania. And that's how they could see, this group of attackers are actually working out of the GRU office or the IRA office in Moscow and not someplace else. If you're going to be an attacker on something, you want to be very careful about your moves. Okay, so the attack I want to talk about today is a recent one called DNSpionage. Has anybody heard about this one? No. So the attack was done on United Arab Emirates, UAE, not UEA, and Lebanon. And the goal of this attack was to steal passwords and to be able to and to read people's email. And the way they did this is that as part of the internet, there was something called the domain name system. The domain name system is the service that says when you type in a name like www.google.com, DNS tells you go to IP address 105.24.13.97. So what this means is, for example, if I was able to compromise the DNS server, then when you went to DNS, I could send you to my own machine instead of somebody else's machine. And the first step in launching an attack in many cases is to get someone to connect to your machine. So these attackers figured out how to redirect domain name lookups to their own machines. They could then capture, once they had the traffic, they could then capture email machines. They could decrypt email. So how did they do this? Like, what does it take to launch an attack like this? So first of all, they had to figure out how can you hack into DNS. So, DNS is managed by these companies called registrars. You pay them, some amount of money a year, and they will record that www.google.com belongs to Google. And the security that they have is often not that great. Because how do they know, for example, if I call up and say, I want to make Google go to my IP address, how do they know that it's me and not Google? they don't have a great way of knowing who owns a domain name. And so it's not impossible to sort of convince one of these things. The other thing is these are just companies with computers. And so you can break into a DNS registrar, infiltrate their computers, and then redirect traffic. The other thing is that we have this mechanism called secure sockets, or SSL, also called transport layer security, or you see this as HTTPS with a little lock symbol in your browser. This is to make sure when you connect to a server that it actually has the right certificate, that it has the right secret key to let you connect. This is supposed to directly prevent attacks like DNS hijacking, where somebody sends you to the wrong server. So what they did is they figured out how to get a certificate for the domains they were hijacking, which meant that any client connecting them would believe they were the right domain. Now there's another mechanism that is trying to prevent this, to sort of secure DNS itself, called DNSsec. DNSsec puts certificates right at DNS. So when you go to DNS and ask to look up a domain name, it's supposed to send you back the information with a certificate that says this is a good mapping. And if clients validate this, and an attacker doesn't have the keys, it's hard to do DNS hijacking. So it turns out that the attackers here broke into one company that was a DNS registrar, and they also figured out, they found a company that generates certificates called Komodo that wasn't very secure, and they were able to get Komodo to issue them certificates for Lebanese and Emirati websites. So once they could redirect traffic to their servers, all these people in Lebanon and United Arab Emirates, when they connected to get their email, would connect to their server. They would validate the certificate. It looked secure. They'd log in. The attackers would snoop their passwords. When they downloaded mail, it was encrypted with keys the attackers could see, so the attackers could see all their email. For a while, they were able to read everybody's email. Now, ultimately, people figured this out, and people figured it out because they could see that there had been changes in the DNS records of where these servers were that looked kind of suspicious. And they could see that the attackers didn't always redirect traffic. They only redirected traffic for an hour at a time and then snooped a bunch of passwords and then redirected it back. So security researchers could see this redirection happening periodically, which looks kind of suspicious. And so they're able to figure out what's happening, and I think they were able to put everything back in place. But it's sort of an example of the kind of attacks that go on in the real world and the sort of different components that go into it. Any questions? No. Okay. So we're going to pick up now where we were, talking about defenses against stack smashing and heap smashing attacks. The things we've talked about so far last time were non-executable memory pages, the WXORX policy. We talked about return into libc exploits and return-oriented programming, where you don't put any code in, you just sort of put in a bunch of addresses you want to jump to. We talked about address space layout randomization as a defense against that. So what we're going to talk about today are some more defense mechanisms that attempt to sort of further address the problem. So as a quick recap, you've seen this a bunch of times, just to remind you what your address space looks like. At the bottom, text data, uninitialized data heap. At the top, environment variables and stack. As you probably know by now from doing the project, that where the stack starts depend on the size of your environment variables. If you have very small environment variables, your stack starts higher address, lots of environment variables, it starts at a lower address. So it's really the same space is used for both. On our stack, we have this standard stack frame. And again, this is historical stack frames. Modern stack frames look a little different, where we've got the caller local variables. So like in your main function, any variables you're pushing on the stack to call somebody, temp1 and temp2. Then you have your saved instruction pointer, your saved frame pointer, and then you have your local variables in the call leave routine. And again, our attack works by overriding the variable in the call leave routine to overwrite the frame and stack pointer. Okay, so the WXORX policy said, we can't really prevent you from overwriting your stack, but we can make sure if you overwrite it that you can't put code into it because we will not execute that code. What we're going to talk about today is what can we do to try to prevent people from overwriting the stack. Now, one thing to note, it's very hard to use memory protection to just say you can't overwrite the stack. Why is that? Why can't we just make the stack, parts of the stack, read-only? Yeah?
This is because there's nothing in the hardware that stops us from going anywhere.
Well, you're right, there's nothing in the hardware to do that, but suppose, we've got people here who are computer engineers. They can design hardware, potentially, to stop you from writing things to the stack. Is that a reasonable solution? Any thoughts? Yes? Right, so the basic point is that the stack is there for temporary variables, so your program is reading and writing from the stack all the time. Every time you make a procedure call, you have to write your saved address and your frame pointer to the stack. So the program has to write to the stack in certain cases. It just doesn't want to sort of overwrite it in certain cases. So it's hard in hardware to sort of enforce that sort of very fine-grained policy of what is writable and what is not writable and when it's writable. We will talk later about how we can actually do that. But for now, what we will look at is what can we do to at least detect when the stack has been overwritten. Because suppose somebody overwrites EIP. If we detect that EIP has been overwritten before we jump there, then we're not being attacked, and then we can stop the attack. Because the attack starts as soon as we jump to the address and save EIP. So if we don't ever do that jump or that return instruction, then we don't actually fall prey to an attack. So the solution people come up with is something called a stack canary. The word canary comes from a practice Welsh miners had of carrying canaries with them into coal mines. And canaries were very sensitive to coal gas, and so that if there was a dangerous gas buildup, the canary would die, and the miners would know to get out of there before they died. So similarly, we're going to put a canary on the stack. If the canary dies, then before the program dies, we want to sort of take some recovery action. So the idea, this is called stack guard, is that we are going to write some value onto the stack before the important saved data that is vulnerable, the saved frame pointer EBP and the saved instruction pointer EIP. So we are then going to see if this value at the end of a function is the same as it was at the beginning of a function, then we believe that our saved important data hasn't been overwritten. Now, one quick question, why do we think this will work, right? Can't someone just skip over the canary and still overwrite EBP and EIP? Yes?
Because they don't know what's in there.
Well, so they don't know what's in the canary, so if they write to the canary, they will mess it up and it'll be detectable. But is there a way they can skip over the canary and write to later addresses and not modify the canary? Yes? Why not? Yes?
If you know what there is, you can just rewrite the same values.
Okay, so there's two things. So one, the reason it's hard is because when the buffer overflows we looked at are taking a local variable and just contiguously writing off the end. Like strcopy, memcopy just writes contiguously, it doesn't skip over values. So that makes it hard to skip over the values that you want to protect. And then your comment was, well, if you know the canary value, can't you just fix this? So that kind of gets to the question of how do you construct a canary value? So one option is that you can construct it in the kernel when you boot the system and have a single canary that everybody in the whole operating system uses. How would this be effective or not? Any thoughts? Or when would it be effective? Would it ever be effective? You're shaking your head. Why not?
You just like, for instance, get a user account, just run GDB and like find out what it is for one process.
Okay, great. So if somebody can log in locally and run any program, they can figure out the canary value. But the flip side is if somebody's attacking over the network and they can't run a program, then they wouldn't be able to find the canary, and it might be secure in that case. If you're worried about people connecting over the network to a web server and injecting data. So in that case, it might not be so bad. What about choosing a single canary value for a whole process? When you start the process, you pick a canary value and use that. How is that for security? Any thoughts?
So for the web server example, just all the threads should have the same canary value.
Yeah, so all threads would have the same canary value in that case.
And the network might probably probe and guess what's the canary value.
Okay, so in that case, right, you could probe for the canary value, And you would keep crashing the system as you probe, or you would certainly be detected, because whenever you probe, you get a wrong number. The other problems with probing is your canary value can be 32 bits, or you can make it bigger, right? There's nothing that limits you to a 32-bit. You could have a 64-bit canary. So random probing is unlikely to actually yield anything. Other thoughts on having a single canary for the process? Can you think of any attacks that we talked about that might make this vulnerable? Yes? Right, so how would a format string vulnerability potentially defeat having a single global canary? Right, so with printf, remember with printf, we can cause printf to just print out whatever is saved on our stack. So if we put in a format string that has a whole lot of %ps, it will dump out everything on the stack, including that canary value. So at that point, we can learn what the canary is if we have a format string vulnerability, and then use that to attack the same long-running program later using a buffer overflow with that canary. So for that reason, people have looked at or have tried to build systems that will use a random number that changes on every function call. Any thoughts on upsides? I mean, that sounds more secure. Can you think of any downsides of an approach like that? Yes? Right, so it's definitely slow, like coming up with a good random number on every function call. Instead of just pushing some things in the stack and jumping, you now need to find a random number somewhere. So that will certainly can slow things down. There's another problem, which is that where do you get your random numbers from? Typically, you make a system call to get random numbers. And so how do you make that system call in advance of having random numbers? So you need to actually have libraries loaded that have your random function in it and start executing code before you can start applying this technique. So it's sort of a challenge to figure out where your randomness comes from all the time when you're applying this. Because you can't just have the kernel sort of provide one value to everybody. So there's another thing you can do, which is there are ways to sort of skip over canary when there's a copy operation. And the way you would do that is take advantage of alignment restrictions in C. So if you have a structure that has like a character and then a double, what C will do is it will lay out it'll make sure the doubles align to an 8-byte boundary. And so this space here is all empty. And in some cases, if you do an assignment, the compiler will not actually copy this space here. And so you can get lucky, and if there's holes inside structures that you're copying around, you might be able to skip over a canary sometimes. It's not as likely a bug, but there are bugs like that you could handle. So there's some other things that you can do. So that was StackGuard, and this adds about 8% overhead on Apache. There are sort of more things you can do. ProPolice has sort of a fancier version of this. So one thing you can do is add protection for registers, because there's a problem that if you save registers, you're supposed to restore them properly. So you can actually make sure the registers are properly restored. So one thing people have done is they have basically encrypted, instead of putting a canary there, they will basically XOR the return address with a random number, and then XOR it again afterwards. And what this means is that if you change the instruction pointer, it'll be XORed with some random number, and you'll jump to some random location. So you can't predict where you will jump. You will take the attack, but you'll jump in the wrong place. So that's another approach of protecting the return pointer. Finally, something else people have done is they've realized that the biggest problem comes when you have an array right next to your frame pointer and stack pointer. Because if you overwrite the array, you overwrite these, nobody detects it. And then you might have other local variables further on the stack. So what Propolis does is says, well, what we want to do again is detect problems as soon as possible, so you crash early instead of suffering from the attack. So what Propolis does is it puts all the non-array variables on the stack first, so that if you overwrite the array, you'll overwrite these other local variables before you overwrite the stack and frame pointer. And this means that you're the chance of having some kind of crash or failure because you corrupted these is higher, so you're less likely to actually jump to the corrupted frame instruction point. So, sometimes it helps. It doesn't work perfectly, but it doesn't really cost anything. You're just changing things in memory, but you're not adding any extra code. And so it has some benefit. Yes. So if you have a heap overflow, it's true you can write anywhere in memory. So that's one way to bypass it, is that with a heap overflow, you can directly write, if you know where a return address is in the stack, then you can totally bypass this. So that the approach where you encrypt the return address doesn't work, because in that case, you will sort of decrypt it before returning, and so you can't be sure what address you'll jump to. So it does help for this particular case of having a canary. So that is definitely one way you would get around it. Yes.
Also, don't some of these security additions add more potential flaws?
It's true, when you add extra security features, there is a chance that you have more complex code with bugs in it. So there is sort of a trade-off of this sort of economy minimal mechanism and security, and you're seeing that we're sort of adding more and more things in. So we can sort of hope that we're not introducing new bugs. So another way you might get around this is to, where'd my pen go? If we have something like, so if we have a case where we have a buffer and we have a character pointer, and we do these tricks of, protecting the return pointer, and we do the trick of rearranging things, when you overwrite this buffer here, we can overwrite this pointer. And then if there's ever any code that says, something like that, we can control where the pointer points, and then we can write something into that pointer. So if we can overwrite into some pointer value that gets written later, we can't directly modify we're not overwriting the instruction pointer, but we're overwriting a pointer that we now control, and then we can potentially write data through that pointer to someplace else. This is like the heap attack, where we can sort of pick a pointer and pick which data to write there. And so putting in stack canaries doesn't really solve this problem either. So another approach people have taken is to say we're going to have what's called a shadow stack. Whenever you enter a procedure, the first thing we're going to do is copy the stack values, the frame pointer, and the instruction pointer to some other location that is not known to the running code. And then at the return of the function, we'll copy it back. So we'll make a copy someplace else. So basically you have two stacks. You have one stack you execute with, which mostly stores your local variables and your parameters, and another stack that actually stores the true value of your frame and your instruction pointer. And then on a return, you can see if anything changed in the middle. So we don't have to copy it back. We just have a safe value that allows us to check this. So again, the way you would get around this is, one, if you can overwrite a pointer somewhere, then you can potentially overwrite the saved stack value wherever it's stored, if you can find that. You can also overwrite a function pointer where you're calling through a function pointer someplace and not bother with the stack at all. So again, all of these things help. They make it harder to launch an attack. They raise the bar, and they block a bunch of existing attacks that are sort of canned and easy to launch. But they don't necessarily make your code bulletproof. So they're worth doing. You sort of have to do them. Something like this to stop the attack, but it doesn't actually make your program fully secure. So this is the technique I talked about using XOR. Okay, so all of these techniques basically say we are going to either try to protect the information by storing it someplace else, by encrypting it, or we're going to try to detect stack corruption by putting in a canary. Is there some way to sort of make sure that you just really can't corrupt function pointers at all, that you only ever jump to places that the original programmer told you to do? And this is sort of this problem of confinement that I talked about a couple weeks ago in operating systems. We want to confine the code that you're running to just execute what the programmer said to run and not anything an attacker injects. So there's a couple of techniques we can use for confinement. One of the easiest things we can do is we can do what's called changing the root directory of a program. What this does is say when you open a file, the slash, sort of the slash in your path name at the beginning is no longer the root of the whole file system. It's somewhere in the middle of the file system. So if I say chroot/temp/guest, and then I run as guest, this means that when the guest sees things, it will only see files that are underneath temp/guest, meaning that it can't see my files under /etc password. And so it will, I can make sure then that it can't sort of access files I don't want it. So if I want to download a program from the internet, make sure it can't see my homework, I can run it in some temp directory. It can only see files in a temp directory and can't see my homework files using this approach. So there is a, so for example, if the program tried to open etc password, it would open some temporary version of etc password. The downside with this is I really have to have a copy of everything a program needs to run. If you've ever run strace on a program, it will print out all the files that your program loads while running, and it's pretty stunning how many files your program will open, because it'll open all these shared object files like glibc. It also turns out there's a lot of localization, sort of translations of error messages into whatever your language is that get loaded. So there might be dozens of files that have to be present to actually run a program successfully. Yes?
Would it be easier to lock away files you don't want read?
So you could try to lock away. The problem is, how do you know exactly which files you don't want read? So it's easier, this is sort of the case of secure defaults. It's easier to say, I'm just going to give it access to the things I want, than to say, let me look at every single file and decide if it's risky or not. So you're absolutely right, it could work. So there's another problem, which is that all this does is change what you can access in the file system. Yes?
Are we assuming the user or the attacker doesn't know that it's in this separate directory? Couldn't they just do ///?
So a good implementation of chroot will not let you, will basically redirect .. in the root directory back to itself. So it will preserve, I mean, if you could, some implementations of chroot have that you can escape just by doing .. But a good implementation will prevent you from doing that, because you're right, it could actually do that. And that is one way that, I mean, there are ways of escaping, people have escaped jails in that way. But then people fix the operating systems. Okay, another problem is there's no limit to the network access. So whatever program you're running can connect over the network, download arbitrary shellcode, probe for bugs in your operating system, which is not necessarily what you want. Another problem is that, this is the problem that was just brought up, that if your chroot doesn't work properly, then you can put in .. and it will redirect someplace else. Another problem, which is a little more subtle, is that you can sort of fool setuid programs. So suppose you create your own copy of etc password and etc sudoers. So sudoers is the file that says who is allowed to run sudo to sort of do some privileged operation. You then chroot to some jail, and then you run a setuid program. that setuid program might see the wrong version of etc password. So if you put some corrupted data in there, then etc password will read the corrupted data that it wouldn't normally read and perhaps suffer an overflow. If you call sudo, then it will read the wrong version of the sudoers file and will potentially give you access instead. So the key here is that if you run setuid programs, you can make them run without their input files, but with input files you choose, which would be the wrong files. And so this could sort of give you access to what that code is doing. So this is, again, not sort of this is sort of risky thing to rely on. So let's think about other things we can do to sort of confine a program. So another thing is to think, well, when we have a risky program, if it actually wants to escape the process and attack your system, it's going to have to make a system call. For example, your shell code is calling execve to run/bin/sh. So can we, instead of worrying about what the code does inside, worry really about what can it do outside of the process to the rest of the system? So one way to do that is to have a monitor that is called on every system call your target process makes that can then decide, should this be allowed or should this not be allowed? So this is a layer of protection above what the operating system has that lets you have finer grained control. So for example, you could say for this particular program, it should only access this one file. It shouldn't be able to call over the network. It shouldn't be able to figure out call get time of day. Any system call that it makes, we can then control in this monitor, even though the underlying operating system doesn't have any way of controlling this. So this is a way of adding extra protection onto the system. So there's a system built at Berkeley called Janus that does this. So you have some process that's running. When it makes system calls, they are sent to another piece of kernel code that will then send them up to a user mode piece of policy code that will then make a decision, do you allow access or do you not allow access? And it will then tell the kernel you should allow access or not allow access. And you can write policies that will say, for example, this program could only access files that end with a certain extension. Like an image viewer should only be able to view .png, .jpeg files and nothing else. Or in a piece of software from Adobe should only be able to connect to websites or DNS names that end with adobe.com and nowhere else. So we can add policies that restrict what code does in this way. The cost of doing this is that you have to, every system call has a couple of extra context switches and system calls built into it. But there are other things questions you might have about this or issues you might see in this kind of design. Yes.
Yeah, really slow it down. We can spam it with syscalls.
So if you have a program that is spamming your system with syscalls, that program, the performance of that program wasn't relevant to you because it's an attacker program. The programmer could the same program could slow you down by just sitting there in an infinite loop doing nothing. So it's true it'll slow. If there's an attack program, it'll slow that does intentionally expensive things. That program. The performance of that program doesn't matter. What's more important is a valid program that you're running that you slow down when you don't want it to run more slowly. Yes?
What if the target program already has a position to make the syscalls that exploit
Okay, so there's a problem that it might be that you can't tell good behavior from bad behavior because the system calls that it's making it's already allowed to make. So one option is, can you look at the parameters to the system call? So if the program's allowed to call execve because it's launching, a helper program, maybe you can say, I'm not going to allow executing anything under /bin or /userbin, only things in the same directory here. So you can restrict based on the parameters to a system call to be a subset of everything that's allowed. So you're right, just the system call itself might be allowed, but then we have to go finer grain. Any other thoughts?
So we also need to protect the communication between the Janus and the off-Janus,
Yes, so Janus in mind we need to protect because if you spoof and run the wrong policy engine, you could sort of allow everything. So we do need a secure way to sort of launch Janus and connect it. So it turns out one of the biggest problems in systems like this is sort of figuring out what is the right policy. This kind of gets to what you were saying, which is how do you know for a given program you download off the internet that you actually want to run, or a program in your system, what is the complete set of things it should be allowed to do, right? So if you have, if you want to protect Etsy password, the password program, how do you know exactly what that password program should do? So you could run it, see what it does once, and say, okay, we're going to grant access to the Etsy password and Etsy shadow files, and that's it. But password might take a dozen different command line parameters that cause it to do lots of different things. And it might access lots of different resources based on the parameters you pass in. And so there's a challenge that writing a good policy here that sort of lets you have access to just the things you can have access safely and none of the things that are unsafe is a hard problem. For existing code, if you have new code, it's not so hard. And that's why this approach works well for things like applications on phones, because applications on phones are all new programs. So you can, so Apple and Google can tell developers you can only write programs in the style that we can protect, and you can't do things that we can't protect. So we're now actually going to switch to a quick example. This is something called Google Native Client, and this is an example of applying this approach. This is something Google built. They don't use it anymore, but the idea is they want to be able to take more or less any C program and run it safely. And so they had to think about how do we let an arbitrary C program run and really make sure that it can do no damage to our system. So you might example, you want to download a game from the internet, run it. You want to run it as yourself to access your files or something, but you don't want it to sort of do things that are too bad. So what it does is it actually creates, first it creates an operating system level sandbox. Well, here's an example of if you have an extension in like a browser extension, like your Flash player or something, you might want to run that in some kind of sandbox. So if there's bugs in Flash, it doesn't corrupt your whole system. So it's going to create a multi-level sandbox. And a sandbox means some confined environment where there's a lot of things a normal program can do that this program can't do. So one of the things it does is it says when you compile the code has to follow a particular style. So one thing it says is that all basic blocks have to start on a 16-byte boundary. So this means that all addresses you could possibly jump to or return to are on a 16-byte boundary. So this means that you can never jump in the middle of an instruction sequence because they're not be aligned on a 16-byte boundary. And we can now analyze all the assembly code in the system to sort of see if it's safe. So that gives us control over what instructions actually get executed. The other thing we are going to do is we are going to scan the code. Before we load the code, we're going to scan it to see, does it follow this restriction that everything is on a 16-byte boundary, that all places you jump to are valid multiples of 16. If we see any invalid instructions that we don't trust or we think are risky, we can just fail to run the program. So this is a model where we're not doing sort of totally unmodified programs, but we're willing to say there's some things you just can't do. The other thing that it does is it will restrict user data to sort of the lower portion. Any data you allocate, your stack or your heap, anything writable is in the lower portion of your address space. The code is at the top. What this means is that every address that you write to can now be masked and sort of either checked to make sure it's in the lower portion, or you can mask it and turn off the bits for the upper portion. So you can make sure that it's only accessing the data you want to have access to. So if your sandboxing system is sort of storing some of its own private data up here, then the code that's running can't access that private data. So this sort of separates things out. So this is what we do inside. And so this protects things because we can now make sure in terms of like return-oriented programming, you can't sort of jump to arbitrary gadgets in your code because we're controlling where you can jump to. And we're going to modify the code so you can't jump. So overriding the stack will be more difficult because we now have control over where your data is and we're checking data access. The other thing that happens is that Google Native Client uses something like Janus to actually monitor all system calls and to apply extra checks on those system calls to make sure that they don't do any system calls they're not allowed to. So this means there's sort of an inner sandbox at the code level and an outer sandbox at sort of the operating system level that locks things down. And the result, this is just some arbitrary data, shows that, if you have a bunch of high quality engineers working on something like this, your performance is what, 5%, 6% slower. So it doesn't have to be that expensive to get sort of a very secure system. So this raises the idea of sandboxing code by sort of putting code in an environment where even if the code has bugs in it, is malicious, that it can't affect the rest of your system. So Native Client does that by, one, to make sure the code doesn't have bugs in it through rewriting the code. The second thing is the sandbox that monitors system calls. But another approach we could take is to use a virtual machine. So, we could, for example, this is sort of a classic virtual machine where we have a host operating system, Linux or Windows. We run a virtual machine monitor that presents virtual hardware, and then we run applications on that. So this means that if we sort of have our root control or the things we care about in one virtual machine, then anything running in the second virtual machine is isolated from the first virtual machine. So we can make sure that, if we have buffer overflows or things like that in VM2, anything in all of VM2, they can't corrupt anything in VM1. So this can prevent sort of, certain things from happening. So it turns out that virtualization is, it's good and it's used, but there's also ways to use virtualization to attack. So there is a system called the Blue Pill, named after the Matrix, as you can guess. And the idea is, what would happen if I surreptitiously snuck a virtual machine onto your computer and then booted your guest operating system in that virtual machine? If the virtual machine does a good job virtualizing hardware, you may never know there's a virtual machine running on that computer because it can give you access to the GPU to draw things, access to devices, but under the covers at the very bottom, there is this code that I provided. And anything you do, any antivirus software won't see it because you're inside the virtual machine. So this allows me to write sort of a stealth virtual machine, a stealth virus rootkit that's on your system, and you can never detect it because you are living inside its virtual world. And so there's a woman who developed this and demonstrated it, and there are defenses against this as well, which I'll let you think about. So this kind of concludes our discussion of low-level security defenses. Some things to think about are is the native client approach of sort of rewriting code and heavily sandboxing everything the right way to go? Or is VM-based sandboxing where we sort of give every separate program we care about its own virtual machine with its own virtual hardware that is very strongly isolated? Pardon me. Another thing is, how does this make you feel about the computers that you use and the trust you place in them, with your passwords and bank accounts and everything else that you do? Like, does it make you feel good that there's all these defenses, or does it make you feel bad that every defense we have, there's lots of known vulnerabilities in? Okay.